Superconductors are special materials that can levitate over magnets and conduct electricity without losing any energy. However, in order to understand superconductivity, we must first understand what current and resistance are. Current is a flow of electrons through a material, usually a conductor. Conductors, including superconductors, consist of a periodic structure, or crystal lattice, of positively charged ions surrounded by a sea of electrons. These electrons can be pulled from one end to the other by an electric field, creating current. But most conductors are not perfect conductors. This is because they have resistance. Resistance is the opposition to the passage of current, or electricity. This resistance often causes the current to lose some of its electrical energy as heat. Lattice vibrations due to thermal energy cause collisions of electrons with the lattice. These collisions act as obstacles to the electron and cause a loss of electrical energy as heat, making them a primary source of resistance. To get a better picture of how lattice vibrations create resistance, let's compare resistance to walking across the room. You, represented by the red dot, are like an electron. The other people in the room, represented by blue dots, are like the lattice structure. You want to get from one side of the room to the other. How do you, like an electron, travel across the other side? You start walking in a straight path. However, the other people begin to move around and get in your way. You bump into them and get pushed off your straight path. Bumping into a moving crowd is similar to electrons colliding with a vibrating lattice. You slow down from bumping into people, just like how an electron would lose energy moving through a material with resistance. But if the other people never left their original positions and lined up in an orderly fashion, you can easily get from one side of the room to the other. This is like a material with low resistance. That is why resistance decreases at lower temperatures. When cooled, the lattice of the conductor starts to freeze in place and vibrates very little. Just like when the people are not moving around in the room, fewer vibrations create fewer collisions and, therefore, less resistance in the solid. But superconductors behave differently. Superconductors are materials with zero electrical resistance. Like a normal conductor, resistance slowly decreases as the superconductor is cooled, but when it is cooled below its critical temperature, its resistance plummets to zero. Critical temperatures are different for each superconductor, but are usually around the temperature of liquid nitrogen, which is minus 321 degrees Fahrenheit. For comparison, your freezer is cooled to only 0 degrees Fahrenheit. This sudden drop in resistance is due to the formation of Cooper pairs. Cooper pairs are two electrons that travel together in a superconductor. To truly understand why Cooper pairs form and how they contribute to zero resistance, you would need to know some quantum mechanics. But you can get a rough idea by looking at the lattice structure. As an electron passes by, the positive ions of the lattice are drawn inward because positive and negative charges attract. This creates a temporary region of concentrated positive charge, which pulls the second electron toward the first. This ultimately allows the two electrons to form a weak bond. Because the superconductor is so cold, there is not enough thermal energy to break the bond in the Cooper pair. This prevents the scattering of electrons, which would have otherwise resulted in resistance. Zero resistance allows superconductors to be very energy efficient. When conducting, no electrical energy is lost, making superconductors an ideal material for transmission lines and energy storage. Superconductors can also be used for magnetic levitation. As we learned earlier, superconductors must be cooled by liquid nitrogen before it becomes superconducting. When cooled, magnetic fields can no longer penetrate the superconductor. This is because the outside magnetic field induces another magnetic field within the superconductor that perfectly opposes the outside field. The two magnetic fields repel each other, allowing the superconductor to levitate. This phenomenon is called the Meissner effect. When we place a superconductor over magnets, the Meissner effect causes the magnetic field to change and form a magnetic cage around the superconductor. This cage locks the superconductor in place, allowing it to hover over the magnets. If we use a series of magnets, then we can extend the cage to make a tunnel that the superconductor can travel through. People are currently utilizing the Meissner effect in magnetic levitation, or maglev trains. These maglev trains magnetically levitate over the train tracks and can move over them without any friction, allowing them to reach speeds of over 300 miles per hour, twice as fast as the quickest Amtrak commuter train. Unfortunately, superconductors are seriously limited in their uses because they only operate at extremely low temperatures. Keeping them cooled with liquid nitrogen is extremely expensive, so researchers are still looking for higher temperature superconductors. To summarize what we learned today, The formation of Cooper pairs allows superconductors to have zero resistance. The Meissner effect allows the superconductor to eject magnetic fields and levitate over magnets. Superconductors can be used in many applications, including maglev trains. But before these applications can be realized, we need young minds like you to find higher temperature superconductors that can be produced cheaply and efficiently. Just imagine a car made of superconductors at room temperature. It would be able to hover over magnetic roads and move without ever touching the ground. Room temperature superconductors would allow us to satisfy one of society's ancient dreams: defying gravity.